Hi. All right. So the purpose of this video is to help B-Block, because I'm going to be gone on a field trip, cover basically the material that you need in order to do the advanced Lewis structure worksheet. Also, anybody else who missed class, like just before break, this will go back over all of the notes that we did on Friday before break. Okay. So what we're going to work on is drawing Lewis structures that have exceptions to the octet rule or have resonance or are ions. And we're also going to work on formal charge. Don't worry. I'll explain formal charge when we get to it. So remember warm-up number 5. You probably already have this in your notes. Trying to draw the Lewis structure of this compound. Remember how things are organized when you have written like this. Carbon has the atoms after it usually attached to it. And then the next carbon has the atoms after it attached to it. So we got two centers then because we got two carbons. So we count up our valence electrons. We have 18. We try to organize it around the two centers, sticking the things immediately after it on the previous carbon. And then we got to realize we'll probably have to connect the carbons together. Put in 5 bonds. That knocks off 10 electrons, leaves us with 4 pairs. We put our 4 pairs on, and now something happens. The chlorine's full, but this carbon has 8, but this carbon only has 6, so that's a problem, all right? So when we're short a pair of electrons, we have to go to rule 6 and add a double bond. All right, now, this structure, we're going to come back to when I talk about formal charge. Formal charge is the mathematical way to determine whether or not you have the correct Lewis structure. And I'll show you 2 different versions of this compound, one of which will have the right Lewis structure and one which will have the wrong, and formal charge can prove which one is the correct. Okay, now exceptions to the octet rule. We have 2 types of exceptions. We have one type that have less than a full octet. Now, so when you have molecules of beryllium or boron that contain those as the center atom, beryllium is perfectly happy with 2 fluorines or chlorines bonded to it, single bonded to it with no lone pairs. Boron is perfectly happy to have 3 fluorines or chlorines single bonded to it with no lone pairs in the boron. That means beryllium will have 4 electrons around it. Boron will have 6 electrons around it. Both are less than a full octet. So here's just sort of a schematic that shows that. Just remember, instead of the X's for electrons here, you could draw lines. Here, instead of the X's and dots, you would draw lines. That's the way we do it in America. This is an older IB Chem slide. Okay. In addition to those 2, beryllium-centered, boron-centered small molecules, we also have some that have sulfur or phosphorus centers, which are quite a bit bigger, and they can actually have expanded octets. So the ones that we have to worry about are sulfur hexafluoride, sulfur tetrafluoride, and phosphorus pentachloride. These violate the octet rule by having more than 8 around them. They're sometimes referred to as large period 3 element centers. So again, the sulfur is in the center or the phosphorus is in the center. So here's an example of the sulfur hexafluoride. And I want to point out that one of the things, because this is a very busy picture, right? There's lots of lone pairs in the fluorines. One of the things that students do is they forget to put the lone pairs on, the halogens. Your Lewis structure will be wrong because it won't have the right total number of valence electrons shown. So always remember to stick all your lone pairs on. Now, these 3 molecules have expanded octets. So sulfur tetrafluoride and phosphorus pentachloride have 10 electrons around the center atom. The sulfur hexafluoride has 12 electrons around the center atom. So these are exceptions that have more than an octet. Now, some atoms will never violate the rules. Hydrogen will never violate the duet rule. You draw a line to hydrogen, it's done, okay? It's full, it can't form any more bonds, can't have any lone pairs. Carbon, nitrogen, oxygen, and fluorine also will never violate the octet rule. Sometimes we just refer to it as CNOF. They're all 4 in a row, okay? They're never going to violate the octet rule. So if we look at these structures, we did this in class, so hopefully you remember, we ought to be able to pick out which ones are incorrect. This is an easy one. There's 5 bonds to the carbon. That means there's 10 electrons around it. So that one is clearly incorrect. There's one more that's incorrect. If you remember from class before break, it's this one. Why is this one incorrect? If you count up all the electrons, there's 20 electrons around it. All right, but oxygen and sulfur are both in group 16, which means each has 6 electrons. 6 times 3 is 18, not 20. So I just dumped in a couple of extra electrons. So that is also an incorrect structure. Now, I'm going to look at structures of ions. The simplest are binary ionic compounds, which means 2 elements. So let's look at those first, okay? Super easy to do. You put brackets around the metal ion. You put the element symbol in the middle of the brackets. There's no valence electrons, and you put the charge on the top right outside the brackets. For the nonmetal, you also put it in brackets, but you give it a full set of 8 valence electrons, so 4 pairs. You still put the charge outside on the top right. Remember, the metal ion will have a positive charge. The nonmetal ion will have a negative charge. If for some reason your binary ionic compound has more than 2 atoms in it, like for instance MgCl2, you have 2 nonmetal chloride ions, you have to draw both. Here's an example for magnesium sulfide. Again, metal symbol in the middle, brackets around it, charge outside, no valence electrons. Here, the nonmetal of magnesium sulfide, this is a sulfide ion, so it's got all 8 electrons filled around it, brackets, and then a 2- charge. Okay, what about polyatomic ions? So the rules are the same in some ways for polyatomic ions. That is, we still have brackets and the charge outside on the top right. All right, we have to have the right charge on it. But inside the brackets, it really is a covalent compound. So we use all the kind of normal ways of putting together our structure. In other words, it's just like drawing something without a charge, but then we're going to add the charge at the end. So we still have to add up our valence electrons, just like before, but because of the charge, we have to subtract electrons due to the positive charge, and we have to add electrons due to the negative charge. Here's an example with a positive charge. So let's look at the valence electrons. 5 for the nitrogen, 4 for the 4 hydrogens, but it has a +1 charge, so we subtract 1 electron for that. So instead of having 9, it's got 8. And remember, I promised you we will always have an even number of valence electrons. Okay, so now we do it just like we normally would. We'd stick the nitrogen in the middle, put the hydrogens around it. We know we have 8 valence electrons. We put in 4 bonds, 1, 2, 3, 4. That used up all 8. There's nothing left over. We put our brackets around it in the charge. And if you take a quick look, I mean, this is a perfectly good Lewis structure for a polyatomic ion, for this polyatomic ion anyway. Now, we're going to do a little bit more complicated stuff. Okay, we're talking about resonance Lewis structures next. What does resonance mean? Well, I have to show you something a little more complicated. So what we're going to look at is a polyatomic ion that has resonance, as an example. So how does resonance happen? It happens when you're short a pair of electrons. And once you sit there, when you're short a pair of electrons, you look at your structure and you have to figure out where to put in the double bond. If any place you put the double bond, it's the same, it will have resonance. Let me show you what I mean by that. The structures will all look the same, they'll just be differently oriented in space. So first, let's look at the Lewis structure of the carbonate ion. So if we add up all the electrons, 4 for the carbon, 18 for the 3 oxygens, then we add 2 for the negative charge, we have 24. We do it again. Start out like our normal way. We put the carbon in the middle, the 3 oxygens around it, connect our single bonds. That knocks off 6. So what we'd have at this point is 18 left, right? That's 9 pairs. Well, we have to complete the octet. So let's complete the octets on the oxygens. So great. All the oxygens now have full octets, but there's a problem. Look at the carbon. It doesn't have a full octet. Here is where we're going to have resonance. Where do we put the double bond? Does it matter whether we go up, down right, or down left? It doesn't, but that's how we know it's going to have resonance. The reason why what we have to do now is we can't just draw one double bond. We have to show equivalent structures with every double bond that's possible in the resonance structure. So here's one with it going up. We still need our brackets and our 2- charge. Here's one with the double bond going down left. Yes, we have to draw this one. And we have another one that's the same with the double bond going down, down right. All of them have brackets, all have the -2 charge, and we have to put double-headed arrows to show that they are interconverted between these three. So these are all three images of a resonance structure. Now, take a look at your homework sheet, all right? Your advanced Lewis structure homework sheet. There is an example for something called ozone, that's O3. Ozone does not have a charge, but it does have resonance. You don't have to be a polyatomic ion to have resonance, okay? So because it has resonance, you notice that I drew two structures in the example, both equivalent with a double arrow between them, and I did not put any brackets or charge because ozone is a molecule, it's not an ion. Okay, so let's move forward. So you are going to have something like this that you're going to have to do a Lewis structure for in your homework. Now we're going to move on to formal charge. And what formal charge is, it's a mathematical way of determining whether a Lewis structure is correct. All right, so let's take a quick look through this. All right, it's going to tell us whether we have the right structure. I'll go through a bunch of examples, okay? The correct Lewis structure is the one that will have the formal charge closest to zero with any negative formal charge on the more electronegative atoms. What does that mean? Well, it's better to show you how you calculate it and then give you some examples so you can see what I'm talking about. Okay, so here's the rules for calculating formal charge. Fc is formal charge. It equals, okay, we're going to calculate the formal charge on an atom that has things bonded to it. So it's the number of valence electrons that atom normally has minus the number of lone pair electrons plus 1/2 the bonded pair electrons. So this is lone pair electrons. This is 1/2 the number of bonded pair electrons. So this formula is one you're going to need to know. All right, you're going to want to have that sort of memorized. Now let's go through examples. Let's do something simple like water. Okay, so we'll do that right after this. I just have to remind you, the correct Lewis structure will have the sum of all formal charges will be 0 for a molecule and equal to the charge on an ion. And the correct structure will have any negative formal charge on the most electronegative atoms. Those two things have to be true in order for our structure to be valid. Now, let's do water. So here's the formula we're going to use, okay? Here's a water molecule. We got to calculate the formal charge for every atom in the structure, and that's how we're going to figure out if it's a good structure. Let's look at the oxygen first. The oxygen has 2 bonded pairs and 2 lone pairs in this structure. Oxygen has 6 valence electrons normally. So we're going to subtract from that the sum of the other ones. We have 4 for the lone pairs. There's 2 bonded pairs, that's 4 electrons there, and we can take half of that. So 4 plus 2 is 6, 6 minus 6 is 0. So the formal charge of oxygen is 0. If you look at the hydrogen, hydrogen has no lone pairs. The hydrogen atom has 1 valence electron, and a bonded pair counts as 1, so 1 minus 1 is 0. So this must be a perfectly good structure. All the atoms have 0 formal charge. So it's got to be a correct structure. Now, because it's the ones that's closest to 0, all right? Now let's go to something more complicated. I told you I would come back to this, all right? So the question was, some of you drew this structure instead of this structure when I was looking at your warm-ups. You were trying to figure out where do you put the double bond. So which structure is correct? So I'm going to use the formal charge rules and apply it to each structure, and then we'll see. So again, formal charge equals, to pick an atom, the number of valence electrons minus the sum of the lone pairs plus half the bonded pairs. So we have to do the formal charge for every atom in the molecule. If we look at carbon, this carbon here has got 4 bonded pairs to it. That's 8 electrons. The bonded pairs count half, so that's 4. It has no lone pairs. 4 minus 4 is 0. That's good for this one. But what about the other carbon over here? It still has 4 valence electrons, but it's got 1 lone pair, that's 2, and it's got 3 bonded pairs, that's 3. 2 plus 3 is 5. 4 minus 5 is minus 1. Doesn't sound right to me. Now, the hydrogens, just like in the previous example, whenever you have a single bond to a hydrogen, its formal charge is 0. Now let's look at the chlorine. Chlorine has 7 valence electrons because it's in group 17. It's got 2 lone pairs, that's 4 electrons. It's also got 2 bonded pairs, that's 4 divided by 2. So that's 2. 2 plus 4 is 6. 7 minus 6 is plus 1. Now, remember one of the rules was that the most electronegative atom, if there's going to be any negative formal charge, has to have it. Well, it doesn't have a negative charge. The carbon does, and that's less electronegative. So chlorine has a positive formal charge. Carbon has a negative formal charge. This Lewis structure fails. No good. Now, let's look at B. Okay? So again, formal charge is the number of valence electrons minus the sum of the lone pair of electrons plus half of the bonded pair electrons. Okay, so both carbons now are the same. They both have no lone pairs. They both have 4 bonds. 4 minus 4 is going to be a formal charge value of 0. The hydrogens we know from before are 0. Single bond to a hydrogen is always 0. So the only question is, what about the chlorine? Chlorine has 7 valence electrons. Now it's got 6 in lone pairs, so it's got 6 and only 1 bond. 6 plus 1 is 7. 7 minus 7 is 0. Oh my goodness, everybody's 0. This is perfect. So all atoms have 0 formal charge, so this is a good structure. So using this mathematical formula, we could have determined from the warm-up which structure was the correct one if you didn't know how to do it. If you knew how to apply formal charge rules, you could still do it. Now, determine the Lewis structure. So let's see if we can figure this one out. Oh my goodness. Which one is correct? I don't know. Let's see if we can figure out using formal charge rules. We know that they both could exist. Sulfur can sometimes have more than an octet. Here it's got an octet. Everybody's got an octet. It looks like a perfectly good structure. Over here also everybody's got an octet except for the sulfur, which has got 12. I guarantee you the total number of electrons is the same in each and it's the correct number. Not trying to fool you there. Okay, so there's a lot of stuff to add up, but honestly the formal charge isn't that hard to figure out. All the oxygens are the same, so once we know the formal charge on one oxygen, we know it on all of them. So we just need to do the formal charge on the sulfur and the formal charge on an oxygen. So you can see the formal charge on the sulfur is plus 2. It's got 6 valence electrons, no lone pairs, 4 bonded pairs. That'll give us a plus 2. Every oxygen is the same. It's 6 minus 7, so they're all minus 1. There are no atoms with 0 formal charge. This doesn't sound very good to me. All right. If you add these all up, it does add to the correct charge outside. Minus 4 plus 2 is minus 2. So at least that's right. So it kind of doesn't look too bad, but let's see if we can do better. Now, in this structure, the sulfur now has a formal charge of 0. Okay. If you add it up, 1, 2, 3, 4, 5, it's got 6 bonds. That's going to be plus 6 over here, no lone pairs, 6 minus 6 is 0. Your oxygens that have single bonds each have minus 1. Your oxygens with double bonds each have 0. So now let's compare. Here we've got 3 atoms with 0 formal charge. The remaining negative formal charge is on the oxygens, which are the more electronegative atoms. And if you add up all these, it adds to minus 2 or 2 minus. So it's got to be the correct charge, and it is. So our correct Lewis structure is this one. Even though you couldn't figure it out before, now you have a method that you can use to do this. Okay?